and or if you have a PDF or PowerPoint. But at any rate, I'm yours. Please go right ahead. Thank you.
Definitely.
Yeah, I've just started recording, and I can send you this PowerPoint as well, kind of a general write-up of everything. So our company is called Ecophilic, and essentially what we do is something very similar to what all of the organizations that you've kind of linked me to in the last chat. So something similar to what they're doing, but I think in a slightly new way. Sorry. So the two of us kind of head things up within Ecophilic. You met me. Lexington Blood is a partner at a venture capital fund called 7BC, and he's kind of a serial entrepreneur, largely in the biotech space, and we've started a few companies together outside of this as well. So the idea that we had came from this class at MIT that all of us have to take, and it's called How to Make Almost Anything. And the idea there is that if you look at the stuff around you, it was all shaped in some way by a machine, functionalized by maybe some electronics or something like that. But the idea is that with a skill set, software, and machines, you can make anything in your imagination, or almost anything in your imagination. Everybody uses the same machines or similar machines, whether you're an architect or an electrical engineer or a computer engineer. All of that involves shaping materials in some way and then functionalizing them with kind of other smaller machines. So a fabrication lab is just that. It's a building with expert software and machinery. And what happens inside of it is entirely up to the creativity of the people who operate the machines. So these are just kind of some machines that exist in a fab lab. And the main point to take away from this is that there are two main ways of fabricating materials. One is subtractive and the other is additive. Additive would be like a 3D printer where you have nothing on a plate and then you build up from nothing by melting material and placing it in specific locations. And then subtractive would be where you start off with a slab of material and then you etch away different pieces of it until you get the shape that you want. And then from there, microelectronics can be added to make it into a digital device like a phone, or cells can be added to make it into an implant, but ultimately everything that's fabricated is sort of fabricated in a similar way. So this is me in the Autodesk build space in Boston, and I'm working with a couple of robotic arms that you can see there. And robotic arms are nice because they essentially have 6 axes of rotation. They move more quickly and with more precision than a human does. And you can make them into whatever you want by adding a tool at the end of their wrist there. And that's pretty much their use. You add a tool, you make a robotic arm into something like a 3D printer or a metal welder, really whatever you want, but they're kind of very versatile tools. And then back here, you have a water jet cutter that's used for cutting steel and metals and glass and things like that. But this is generally the layout of what a fabrication lab looks like. There may be more or fewer machines, but this is just to kind of give you a flavor of what it might look like. And using the same machines, as I explained before, you can make something as small as this little implantable chip here, which has nanoscale features. And it's a chip that goes into someone's brain, and it can detect little abnormal spikes in electrical activity when communicating between two brain cells. And if it detects abnormalities in electrical spikes, then it will record that event and dampen the signal so that an epileptic seizure doesn't happen. This right here, and this all kind of moves up in scale. This right here is an agricultural sensor. It uses machine vision and various environmental sensors to detect oxygen and nitrogen levels in the atmosphere, nitrogen carbon levels in the soil, pH in the soil, to detect pests as well and spray where the pests are and not all over the plants, which is fairly useful. And then this over here is the mobile version of that. It's a robot that uses machine vision, and it can look at plants and detect which ones are ripe, which ones aren't ripe. It can pick the ones that are ripe. It can also look for weeds and pick the weeds. Over here, you see a robotic prosthetic that was made in the lab next to mine. And this prosthetic up at the amputation site is coated in a special hydrogel that conducts electricity. And the software that this prosthetic runs on, as well as the electronics, are customized so that they can read in electrical signals from the hydrogel, which come from the brain, and then translate that into computer code. So essentially what the prosthetic is doing is it's reading brain signals and translating those signals into motion, just like a normal leg would. So if you think that you want your leg to raise up or walk, your leg will do that. And then this is a plant at BMW where they use robotic arms with various tools attached at the wrist to assemble cars. Some are welders, some are drills, some are just pick and place robots that pick components of the car up and put them into the right place. And then here you see a 3D printed building, and that's about the top scale that you get with a fabrication lab. But importantly, within a fabrication lab, one can make products as well as new tools, new fabrication tools, and that's sort of what my group specialized in. And this is where we get into kind of the unique aspects of our company. And what we propose is essentially an organization which partners with big companies, big international companies like Lego and Ferrero Rocher and BMW and Lexus and Burberry, all kinds of companies that we have connections to. And they will essentially outsource the design, prototyping, and validation of a set of products through a contract. And we, in turn, will staff the team that works on that project, half with experts from our team, and half with community members. And those community members could literally be anybody, no expertise necessary at all. And then in working on a real world project, those community members will gain a certain number of hours on each machine and using each piece of software. That experience will be recorded in a digital profile that can be uploaded to LinkedIn or used in a resume. And then ultimately, once someone passes the threshold number of hours that's necessary to use the machine autonomously, then they can do so and make their own products. And that's really where we focus. We focus on getting community members with no background whatsoever to the point where they can make their own products and start a company within a span of a few months. And in doing that, they can also sort of work with the companies that we partner with, and then in turn, investors get a piece of the contracts as well as points on the back end for each startup that comes out of the lab. So what I want to convey with this image here is this is an area in Colombia in South America that used to be very lush with greenery, and factories had moved in mostly from the US and Asia and sort of pillaged the land, and these people kind of remained, they're indigenous, and they knit textiles to support themselves. And what happens is that someone from Bogota or a main city will come and then buy the textiles very cheaply, and then they'll sell them in Bogota or another main city very expensively, so for a high price. And these people don't see any of that money. But what I'm trying to show here really is that machines do what humans do more precisely and faster. They don't typically do things that humans cannot do. So if you take someone or a group of people like the ones that I just showed in this image here, and you give them access to the tools that you see here, and specifically this is a digital knitting machine with 7,000 needles. Normally if you're knitting, you have 2 needles and it's just you there. And what happens is that this machine reads a digital design file from a CAD program or computer aided design. So you design something and that object, a shirt, a scarf like you see here, whatever you want, is executed by the machine. So the design is turned into what's called G-code, and that G-code is just a series of coordinate points on a defined plane. And what Irmandi did here is that he intertwined nanoscale pressure sensors into the threads that were fed into the machine. And then he wrote software to interpret the pressure signals from those pressure sensors. And that enabled him to turn this scarf that came out of the machine into a piano. And while that seems like just a cool art project, he actually went further. And instead of pressure sensors, he put in nanoscale ultrasonic transducers into the threads that were fed into the machine. And that enabled him to create textiles and garments that you wear that can essentially image the inside of you, like an ultrasound would. So that's really useful if, for example, you go to a doctor and you've been complaining about symptoms, but you don't display the symptoms in front of the doctor can't do anything for you. Whereas if you were to wear this set of clothing, you could say, okay, the clothing sent a video of the inside of myself, my lungs, for example, between 5 and 7 p.m. last night. This is when I was coughing really vociferously. And then, the doctor can see the lungs during that time period and then actually help you. So it was a potentially very impactful project. But the machines that he used and the skills that he drew upon to realize this project are really easily taught. They're the same machines that we all use in a fabrication lab. He wrote some custom software for this, but beyond that, to execute this project would require no more skills than the people in the last image that you saw. You just need an understanding of textiles. You need someone to teach you the computer program that communicates with the machine. You need to learn how to use the machine, and that's it. Beyond that, what comes out of the machine is really up to the creativity of the user. So what we're really getting at here is kind of a factory of the future that has the capability to do semi-industrial scale manufacturing. And that's really useful for our corporate partners who want to see, a prototype. If you scale it up, what happens? Does the prototype behave in the same way, or does it not? Most of the time when you have a prototype of something and then you try to scale it up to manufacturing, all kinds of problems ensue. And so we kind of bridge that gap between prototyping and full-scale manufacturing here. And again, the people who would be operating this semi-industrial scale manufacturing machinery would be community members, and they would learn how to use the machines and then ultimately make their own products. So this is just a video of some of the more complex stuff you can make with the same machines that everybody else uses. This is from my old lab. And what these things are don't really matter. What really matters is that you can sort of make things that look crazy and that have no ostensible limit except for that which exists in your imagination. So that's the idea there. And you can sort of recognize some of those things from the Autodesk build space that I was using. So our partners in this are obviously the UNESCO Center for Peace, the Wyss Institute at Harvard, which is a center for biologically inspired design, things like implants and sensors and medications and things like that. The chemistry department at the University of Cambridge, the Center for Excellence in Biomedical Engineering at the University of Utah, the Engineering Innovation Group, and now the international effort for science and technology at MIT. And then Harvard in general is another partner. So what we would need to execute one of these fab labs, to actually make one of the fab labs, would be somewhere in this kind of vicinity. But what's important to note here is that we don't come with a set of machines to every region and say, these are the machines we have, this is the expertise we have, what can you do with it? We interview people in the regions in which we'll operate, people in government, people on the streets, people in the community, and we see what their biggest problems are and what their biggest foci are in terms of market sectors that they would like to focus on and those that they currently focus on. And then we stack our fab labs with those machines. So each fab lab has different machinery in it. There's sort of a standard set of machinery that every fab lab needs, because ultimately you're going to be cutting down large materials into smaller chunks. You're going to be joining materials together no matter what you do. And then beyond those kind of basic machines, we put in more specialized equipment, depending on what each region needs and wants. So that number kind of changes a bit from case to case, but the rest of these are fairly standard fees that would be sort of involved in every fabrication lab. And that's kind of the pitch. So I'm happy to take any questions that you may have, but that's the idea.
Well, first, could you end the recording so that we can capture just that presentation and then start again?
Sure. Yeah. I think, oh, yeah, there we go.